Hello and welcome. In this example, we are going to look at how to calculate power dissipated in a series circuit. So specifically, we're going to solve for the R1 power. We'll call that P1. So we'll say that P1 is equal to our power law. And so we'll draw out our power law. P on top, I and V on bottom, which means that power is equal to current times voltage. So we'll plug that in. P1 is equal to the current in the circuit multiplied by the voltage specific to this power here. So that's the tricky part. So we know that since this is a series circuit, the current stays the same. There's only one pathway for it, and it's going to stay the same through all of the resistors involved. And so we know that this is only one current, and it has to be IT. So we can find IT and use that against a specific voltage associated with this power, which means that we need to find the voltage drop across this resistor to use that one, right? So we need to know Vr1 to be able to solve for the power through that resistor. And so this can't be just the total power, it has to be R1's voltage drop to be able to get to the R1 power drop. So we can do this using the voltage divider equation, and then we can actually solve for power. We can say that power is equal to voltage times current. And if we don't know current, we can break that down again. And we can say, well, Ohm's law says that the current is equal to our voltage divided by our resistor. So when we solve out for that and reduce it, we get a power law that says that the voltage squared divided by the resistor is going to equal the power. And so then all we got to do is figure out, or keep in line, the R1, and the power 1. So we can use this equation instead of our original power law up here. That means that P1 is also equal to Vr1 divided by R1. We know R1, we know that we can solve for Vr1, and that's going to give us P1. So we're going to use the voltage divider equation to solve for that. So our voltage divider equation is quite handy. It is a ratio equation, and it identifies where voltage drops in the circuit. And so some voltage will distribute across some resistors, and the rest of the voltage will distribute across the rest of the resistor. And by the end of the circuit, down here at the bottom, we should have 0 volts. We should have used it all up by the end. And so we're going to do that using our voltage divider. So our voltage divider says want over have multiplied by our voltage source. And these two wants over have section is going to be what resistors you want and what resistors you have. So what we want is going to be the voltage across R1, which means that we need to want R1 resistor up here. And on the bottom, we have a have, and that's going to be our total resistance, RT. So now we can plug that in, and this is going to give us a ratio equation. It's going to say that we have a total for our voltage to drop across, and we want to identify just a small section of that total. So this equation gets pretty flexible the more you use it. So from here, we know a couple of things. We know R1. We can plug that in. We can say that we got 10,000. We know RT also, it's going to be the sum of the two resistors. And we look at that, we say it's 10,000 plus 32,000. So our total resistance is actually going to be 42 kiloohms, 42,000. And then our voltage source is known also, so we can erase that and we can plug in our 28 volts. Right. And so from here, we can calculate this out and we'll get the voltage drop across that resistor, and then we can plug in directly to our power law. Here we'll say that we have 10 kiloohms divided by 42 kiloohms. I can leave the kiloohms off because they're going to cancel each other out anyway, right? Then I can multiply that by 28 volts, and that's going to give me the ratio of voltage that was distributed to R1. So that means that the R1 power, or the R1 voltage, is equal to 6.67 volts, right? 6.67 volts. Out of 28, R1 burned up 6.67 volts, right? And that means that everything else that's left over out of that 28 volts is the voltage drop across R2. Right? So you could just subtract that. You can say minus 28 volts, and that's going to be whatever's left over across that other section of the circuit. We don't need that though, right? We're looking for the power drop across R1. So now that we got all this, we can go back up to our power law and say that power 1 is equal to Vr1, which we know, right? We just found that at 6.67 volts. We can divide that by the resistor R1 that we know also. R1 resistor is 10,000. So we'll do that. We'll solve that out and we'll say that we have 6.67 squared for our voltage divided by 10,000. That gives us a small little value here, so we'll plug that in. We'll say that we have a P1 equal to 0.00445. We can move that over 1, 2, 3 spots here, and that's going to give us P1. Final answer is equal to 4.45 milliwatts. Right, it's in watts because it's a power value. All right, let me know if you guys have any other questions.